teach you probably the most important idea in grid combi, the most common one. And I'll walk you through the solution of USATST 2011 problem 8. This problem is not that difficult, but it's very instructional in terms of how you use this very, very important technique in grid combi. Uh, yeah, I'm not gonna take away more of your short attention span, and we're just going to go ahead and talk about this problem. So, yeah, and subscribe, please. Just please subscribe because that makes me happy, and like the video as well, or like drop a comment. That makes me even more happy, and maybe I'll smile at some point. Okay. So we have n greater than 1 be an integer, and its be a set of integer pairs a and b with 1 less than equal to a, less than b, less than to the power of n. And we assume that, so essentially, like, we have n is greater than equal to 1, and S is a set of pairs, which means that essentially, like, we don't store integer values in it, we store pairs, like 1, 2, 3, 4, blah, blah, blah. And each pair is such that 1 is less than a, is less than b, is less than 2 to the power n. So they are such pairs that the x coordinate is less than the y coordinate. And we know that the amount of elements in set S is greater than n to the power n times 2 to the power n plus 1. And we want to show that there exists 4 positive integers a less than b less than c and less than d, which are all integers, such that S contains pair AC, BD, and AD are all in S. Before I start explaining the solution, a few instructive moments. When we try to solve a problem, the first thing you always try to do is set up your information as efficiently as possible. That will help you to, like for me personally, my visual analysis is when I present every statement visually in front of me, I can think much quicker of good stuff than if I try to do it in my head. So if that's the case for you as well, a lot of times I would suggest that you try to rephrase the problem in such a way that you have everything present in front of you and you try to classify everything, just break it down so that you can look at the sheet of paper and you know that everything is there. And it's actually I can't like um, pinpoint how crucial it is to actually structure the data that you extract from the problem correctly. If you don't do that, if your extraction of information from the problem is rubbish, nothing good is going to happen. You're just going to get lost. So, in order for that not to happen, I'm I'm going to teach you how to do it the proper way. So, um, let's think, how should we structure this? Because if we try to think about like these random pairs and A B less than B less than C less than D, this is just going to confuse everyone. And we can obviously think about some binary stuff, but at the end of the day, what I want you to think about if you see pairs is coordinate plane. Why? Is because coordinate plane is the best visual representation of pairs, because you just look at it, everything is clear. So that brings us to the idea with the coordinate plane. And for people that are already more advanced, you know that if A coordinate is less than B coordinate, essentially what you will get is kind of like a staircase, like this. You might ask me, what do you mean? If, for example, I take this point here, the this B coordinate, this A coordinate, then B coordinate will be clearly greater than the A coordinate. So what are you talking about? Well, the staircase interpretation is a bit of a modification, and it is true. but it's a bit of a modification because essentially we start our coordinate plane with a being equal to 1 here, nothing new here, going up to 2 to the power n over here, minus 1, because if a is 2 to the power n, there's no such b. And b1, though, is a bit different. So we start b from 2, and we go from the top, and then we go to the bottom, like this. And if you now look at every single point, uh, b will be greater than a, simply because these points are points of equality. They're 2, 2, 1, 1, 3, 3, and blah, 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 blah. So this brings us to that the table is actually of size, this staircase essentially is of size 2 to the power n minus 1 by 2 to the power n minus 1. Sorry if my screen was covering the staircase a bit. I'll try to keep that in mind. So we have this thing over here, right? And we have that this table is almost a power of 2. And what this essentially hints is induction. Because 2 to the power n usually works well to induction, and so does staircases. And yeah, I mean, the cool thing about staircases is if I look at a 2 by n minus 1 by 2 by n minus 1 staircase, so blah, 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 here, blah, 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 2, 2, okay. I won't draw a nice diagram, but you if you try to draw a nice diagram, essentially what you'll end up seeing is that wait, this guy here. Okay. I look at a square, essential square where this is 2 by n and 2 by n. Then both of these will be 2 by, well, there will be staircases of this side, of this size. I'll just draw another for convenience. So then the whole size will be 2 to the power n minus 1. So essentially, one staircase breaks down into 2 plus a square. And therefore, it's quite easy to do induction, and it's quite handy in the sense that uh, we have, if we have greater than n minus 1 to the power of 2 to the power times 2 to the power of n, if we have more than this amount of points here, then we're done because we can just take a, c, b, d, a, d inside this one, and we'll also satisfy the other one. And same story here. So here's this amount of points and this amount of points. And now it's about the time you should have done it probably before this, but it's the time to look at this and understand what does it mean. So what does this configuration actually mean on this diagram? So if a is less than b, that's our first coordinate, so a goes here and b goes here, and c is less than d, so c goes here and d goes somewhere here. What does a and c give us? A goes here, c goes here, that's our first point here. And then we have b and d, so b goes here and d goes here. That's our second point. And then we have a and d. And we notice that there is this nice triangle essentially forming. So essentially, we know that we want to just find a pair that looks, well, a triple that looks like this. And since we already we kind of cut off these triangles, we know that inside the square there is greater than, well, the sum of n minus 1 times 2 to the power of n and n minus 1 times 2 to the power of n is n minus 1 times 2 to the power of n plus 1. And since we want s to be greater than this, then we know that inside the square there's greater than 2 to the power of n plus 1 points. And this square is of size 2 to the power of n minus 1, like this. Uh, Now we're thinking about trying to find the same story, so the same here and here. Another idea, crucial idea you need to know in board problems, problems in Combi, it's called lasers. So essentially from every point or some point, it's a way of doing double counting, but in a less formal way. So you can do it like by shooting lasers out of every single, I don't know, point that is kind of crucial in the problem. And then what you do is you find the amount of intersections between the lasers and some other points, which is essentially double counting, but in a like slightly um, shady way. I would say it this way. So let's imagine that we take every single point, every single of greater than 2 to the power n plus 1 point, and what we do is we draw two lasers like this from each side. This is motivated because we're trying to find these lasers essentially. We know that if I have a point here, at most one of two lasers actually hits another turret. So this means that another laser must hit the board. And we know that if I have a laser here and laser here, only one hits the board and not two of them. So essentially every single tile edge on the board is hit at most once. And we know that at most one, at least one of the lasers from every single point hits the board. Because if none of them, then we're done. We're finished with the problem. So if we have greater than 2 to the power of n plus 1 coins, then we know that there's greater than 2 to the power of n plus 1 lasers that did hit the edge of the board. Because essentially there's at least one from every single turret. Again, if two, if there's at least one that hit the edge of the board, because if zero did, then we are done with the problem. But as you notice on this side, there's 2 to the power of n minus 1, and here's 2 to the power of n minus 1 as well. So yeah, essentially shows that since we had the board initial was 2 by n minus 1, 2 by n minus 1, there's 2 by n plus 1. Well, yeah, we looked essentially here. We looked at the board, which is 2n minus 1 by 2n minus 1 here. We applied the induction for each of these staircases. So we applied that there's less than this amount of tiles. So we wanted to show that here there was, and so inside the square there was a total of, well, the total we wanted to show is greater than n times 2 to the power of n plus 1. And here was n minus 1 times 2 to the power of n times 2, which gives us n minus 1 times 2 to the power of n plus 1. So this 2 to the power of n plus 1 is the total amount of points inside the 2 by n minus 1, 2 by n minus 1 square. And as you can see, we have a square that's of size 2 to the power of n minus 1 by 2 to the power of n minus 1. So, which totals to 2 to the power of n, which is less, obviously. So, that's not enough points